Welcome to today's lunch hour lecture. I'm Jack Ashby from UCL Public and Cultural Engagement, here to host you today. I'm here to welcome today's lecturer, Professor Polina Bayvel, who is Professor of Optical Communications and Networks in the Department of Electronic and Electrical Engineering here at UCL, where she is head of the Optical Networks Group. She's a Fellow of the Royal Academy of Engineering, Fellow of the Institute of Physics, a Fellow of the Institute of Engineering and Technology, and has won a number of prestigious awards for contributions to optical communications technology, which positions her perfectly to give today's talk, The Illusion of Infinity. If you join me in welcoming Professor Polina Bayvel.
So thank you very much. Apologies for the delay. And I've been here in UCL for 22 years, and this is my first lunch hour lecture, so it's a big, big honor. I couldn't give this lecture without acknowledging the International Year of Light, which is just finished. We're in early February, and the 2015 was designated by the United Nations as the International Year of Light to celebrate all that has been achieved using light, photonics, optics, and the technologies that stem from it. And none has been more pervasive than the technology of optical communications, the ability to transmit information using light. Of course, it's not new. Early communications with light included using fire and smoke signals, using heliographs, reflecting sunlight, using reflector shields, communications with boats and ships using an Aldis lamp, and this is a more modern version of the heliograph still used. But they suffered, of course, this is known as free space communications, and it suffers from a problem of bad weather. When there's clouds, there's no light signals. So modern optical communications, and we all use it every time you send an email or tweet or upload anything to YouTube, every time you use a mobile phone, majority of the time the signals travel over optical fibers. And the optical fibers use a principle of guiding of light. And that has been, many of you might have seen this picture. The origins of guiding of light are often attributed to Tyndall, but in fact they arise from the work of Daniel Caledon, who published this principle in 1841 demonstrated in 1841 and published it in 1842 in Les Comptes Rendus. He did this experiment where he took a strong arc lamp, a bright arc lamp, shone it into a vat of water which had a hole in it, switched the lights off, and as the water flowed out, the water has a higher refractive index than air, it guided the light from the lamp along it, and it gave a very beautiful effect. And he didn't think about it for communications at all. He wanted to use it for special effects, and in fact it became known as La Fontaine de Caledon and used in the Paris Opera in production of Faust shortly afterwards. This is often attributed to John Tyndall, who repeated the experiment a number of years later in 1854 at the Royal Institution, but he didn't acknowledge Caledon, and it only became, Caledon's contribution was forgotten, it only became, was rediscovered relatively recently. Tyndall, we won't blame him, he didn't speak French and didn't read the paper, and he was told about this experiment by Faraday. Faraday was suffering from memory problems and traveled to Geneva for treatment, where he saw this experiment being demonstrated and forgot where he'd seen it, then recounted it to Tyndall. The next step in communication was that of the Atlantic Cable project. The ability to contain and communicate over cable was an extraordinary project, the Atlantic Cable project. There are a number of major anniversaries this year, and the first of these is 150 years of the first successful installation of the transatlantic cable. It was an enormous undertaking, probably greater than the putting of man on the moon 100 years later. The first working undersea cable using copper conductor insulated with gutta percha, kind of a naturally occurring rubber, it took place in 1851 between Dover and Calais. And Cyrus Field, a British cable pioneer, and also John Pender, who has a connection to UCL because he gave money to create, to endow and to create a laboratory of electrical technology, which is the modern Department of Electrical Engineering, with Ambrose Fleming as the first professor where I now work, gave a lot of his own funds. All the scientists of the day, Wheatstone, Faraday, Maxwell, Morse, William Thomson, better known as Lowell Kelvin, worked on this project, and it was extraordinary in the determination. In 1857 and 58, the two first attempts failed. The third attempt in 1858 failed after 3 weeks, and it worked at the speed of a few words per hour. The fourth attempt in 1865 the cable was laid by the now commandeered Great Eastern. The cable broke, and finally, under personal guarantee from Pender of £250,000, an enormous amount of money in the day, all British financed. In the fifth attempt, it was a success, and they also recovered the broken cable. And it connected Ireland and Newfoundland over 3,400 kilometers with a communication speed of 8 words per minute. And after that, British cable companies dominated the world. Fast forward 100 years to our next anniversary, 1966. Charles Cow, working in a legendary lab in STL in Harlow, he also carried out his research as an external student at University of London, supervised by another electrical engineering, UCL Electrical Engineering Professor Harold Barlow, proposed glass. He was working on glass, and he proposed glass as a conducting medium, as a medium to carry information.
This remarkable video from February 1966 shows Charles Kao, the pioneer of optical fiber communication, working in the laboratory. It shows him experimenting with a prototype hair-thin optical fiber made of glass. He was part of the British team that first proposed that huge quantities of information might be carried over vast distances by this novel means. This was only the beginning. The transmission loss of these early fibers was so great that many argued that Charles's vision was doomed to failure. However, later that year, Charles and George Hockham published the defining paper which revealed that none of the current imperfections were fundamental.
And in fact, this is 50 years later. This spool contains, guess how much fiber? Anybody care to guess? Go on. So how much? 300 meters. Well, it contains 13 kilometers. 13 kilometers on the spool of fiber. And so this year is 50 years since the publication of that paper. It was really quite a remarkable. At the time, the vision, he proposed the losses of glass were 1,000 dBs per kilometer. He said that if there could be lowered to 20 dBs per kilometer, one could transmit at 1 gigabits per second. Within 4 years, Corning demonstrated 4 dBs per kilometer. The losses are now 0.14 dBs per kilometer, lowest loss demonstrated. So it's a remarkable achievement. And of course, the work, again, in Britain, British-led, the very first systems were put in by British Telecom. Who would have thought it was such a revolutionary company then? Perhaps it's a little bit more conservative now. The first systems between Hitchin and Stevenage were all roughly between 10 and 20 kilometers and carried 140 megabits per second with repeaters every 3 kilometers. This was this was the beginning, within 10 years of publication, of proposal of that paper, first optical fiber systems went in. So, and what's happening now? Well, the growth of optical fiber technologies has completely underpinned the growth of traffic, of digital data. It's dominated by video and social media. And the growth, the internet has grown. This is a projection from Cisco that we all follow. They say that within just a couple of years of now, we will be generating 140 exabytes per month. Well, how much is that? 100 petabytes is the amount of data produced per minute by the new particle collider in CERN. An exabyte, that's 10 to the 18 bytes, or 200 million DVDs, is roughly, 5 exabytes is transcript of all words ever spoken, whatever that means. 1 zettabyte is 10 to the 21 bytes, is the visual information from eyes to brain of the entire human race a year. And no storage system, at least when I looked last, has attained 1 zettabyte. However, the new NSA data center being built in Utah has apparently a storage capacity of 1 yottabyte, 10 to the 24 bytes. What else is driving data growth? Well, Internet of Things, we all have numerous devices connected. In fact, there's more devices now connected than there are people in the world. And that we are now spending more time online than we sleep. And that means much more than being able to connect your toaster from your bed or Googling for your keys. Here is a video from Cisco that shows exactly. I hope the quality is better on this video.
This is the cat that drank the milk and let in the dog that jumped on the woman who brewed the coffee.
Brew coffee.
That woke the man who was late for work.
All right, I gotta go.
And drove the car
Driverless mode engaged.
that found the parking spot
Find parking space.
Parking space found.
that alerted the door that opened the control room,
Hey, Bob.
that secured the data, that directed the turbines, that powered the sprinklers, that watered the grass, that fed the cow, that made the milk, that went to the store, that reminded the man to buy the milk, that was poured by the girl who loved the cat, that drank the milk. The Internet of Everything is changing everything. Cisco, tomorrow starts here.
Actually, the fact that the video is bad, illustrating perfectly my point about lack of capacity, which I'm about to come to. So there was a mistake in this video. When they talked about the data, they showed a satellite. Well, satellites, how much data do you think is carried by satellites? I mean, no, my students are not allowed to answer that. They know the answer. How much data do you think compared to optical fibers? 10%. 10%. In fact, it's less than 1%. There are 250 commercial satellites with 4 gigabits per second per satellite, with 1 terabit per second in total. Global data traffic in 2013, it's much higher now, it's 100 terabits, so less than 1% on satellite. And the bulk is carried in optical fiber. So what do our optical fiber systems look like? They crisscross the oceans and the seas and the land. They're everywhere except probably the very last section the last section from the local exchange to your house, or maybe from green box to your house if you're lucky to have BT Infinity, although it's far from infinite. It is a very finite, very finite speed. So what does it look like? It looks like this. There is a system with a number of lasers which carry digital data. So lasers are very small semiconductor, typically semiconductor devices that are turned on and off electronically at very fast rate. I'm going to show, if I have time, today we in UCL have the press release showing that we've demonstrated, we in our group have demonstrated a transceiver capable of generating and receiving data at 1 terabit per second. Commercial systems generally work at 100 gigabits per second, and there are many hundreds of lasers, each carrying separately modulated data. They're multiplexed together, joined together by a kind of prism device, and then sent along their way over thousands of kilometers, separated by O-beam fiber amplifiers. Fiber amplifiers, they're glass doped with a gain medium, ions that amplify light over a certain bandwidth range, and they're spaced periodically boost the signal, which is lost on the way, between 50 to 100 kilometers. And at the other end, the signals are demultiplexed by kind of inverse prism. I mean, these are all very sophisticated devices that took years to develop. The arrayed waveguide gratings, which are used as multiplexer, demultiplexer, this week were awarded the Rank Prize Awards in Optoelectronics to an international team of researchers, 3 groups that independently developed them. And then they're received and demultiplexed optically. And nothing demonstrates this more dramatically than a submarine system. These systems traverse oceans. There are thousands and tens of thousands of kilometers long, and lying at the depth of anything between 4,000 to 8,000 meters below sea levels. It's quite an engineering feat they're buried typically, to install them, typically buried into the ground and then sent along the way. Each repeater contains an amplifier, and they have to be powered from either side to deliver the power to these amplifiers, and each repeater is about, a human long. I don't know if I can show this video. The videos are not working terribly well. I'm sorry about that. Let's see if it works. Not brilliant, so I'm sorry about that. But it's more just, optical fibers are more just plumbing. It is possible to envisage extraordinary services. It is possible to use wavelengths of light to dedicate particular services that will transform people's life, providing there is sufficient capacity. It is possible to use a separate wavelength for remote medicine, for communication and education, for sensor networks, and for the web with different qualities of service and working over different distances. And one has to develop techniques to intelligently allocate optical capacity and bandwidth as needed. But in order to do that, we need to understand the physical properties of the network and the achievable capacity, just how much capacity can be transmitted. So here is the evolution of what's happened in optical fiber networks from the very early systems I introduced, from the megabits to the petabits that we can transmit now on different wavelengths. And what has happened is that the evolution of technology has progressed at this rate quite fast, until about 10 years ago, when it's become very difficult to make the kind of steps that we've been doing for the last 30 or 40 years. And the gradient of increasing capacity times distance has changed. And so we now need so there's been a range of different technologies that's developed of using different types of fiber, optical amplifiers, many different wavelengths on fiber, coding, amplification, the ability to use different properties of the light wave, which I'll talk about in a moment. But now we need to do something really, really new. And I've put in this gap the logo for our program grant, Unlocking the Capacity of Optical Communications, where we're trying to develop new techniques exactly to negotiate this gap that's appeared. The inability of the technology to follow and track the demand. The development of the technology the development of this growth of traffic has been predicated on the fact that cost per bit has been going down and down. We've been able to make enormous technology stride. That has now stopped happening. And what will happen, that the growth with time, if depending on the amount of data traffic growth, which can be somewhere between 22 and 45% a year, there could be a crash of where demand will exceed capacity. And then two things can happen. Capacity becomes a rare commodity, and it has to be either rationed or controlled by cost. In fact, this cartoon kind of illustrates what will happen. What happens when the internet is full? What will you do? And is there something, what is limiting the growth? So the fiber is very interesting for the physics of fiber transmission is very interesting. The optical fibers, here as you were surprised about how little it looks, but how much fiber there is. is very small. Its core is only 10 microns. 10 microns is a thousandth of a millimeter. That means that whilst the powers of light that are used to carry information are very low, the intensity is very high. In fact, it's so high, it's 1,000 times the intensity of solar radiation at the top of Earth's atmosphere, inside the fiber. And the fiber properties depend on the refractive index. And you all know about the refractive index. You put a pencil into a glass full of water and it bends. Well, that's because the refractive index of water is higher than that of air. And equally, the refractive index of glass is higher than that of air. As you put more intensity in, the refractive index changes with intensity in a nonlinear way. And that means that after distance L, it will acquire phase shift. This nonlinear refractive, due to this nonlinear part of the refractive index, and the nonlinear refractive index will lead to a phase shift and distortion of data. So that's what's happening that's one of the major limitations of the amount of data. We previously thought that we had infinite capacity. This is why BT service is called BT infinity. It's far from infinity. And the capacity is far from infinite that's accessible. And we now have to find new ways of accessing it using different properties of light. So light has a lot of different properties. It has properties that we can use amplitude, phase, polarization, wavelength. So the electric field, unmodulated electric field wave, it's an electromagnetic wave, it carries no information. And it has one frequency, and we can represented by a variation by something called the constellation diagram, which describes its amplitude and phase properties together in one diagram. So here is the use of light of the digital data. You're all familiar. Here it uses amplitude 1. Level 1 means yes bit. Means 1 bit. Level 0 means 0 bit. And it has a certain spectrum, but we can combine it with, we can use also the phase. You can see 0 has a certain phase, and the phase changes at the interface. It goes running along and then changes the phase at the interface, going 0, 1, 0, and acquiring a different spectrum and a different constellation diagram, how the data is represented. And we can combine them together. We can combine amplitude and phase together, accessing more of the spectrum more efficiently. And here is a constellation diagram of what that looks like. Don't worry about the details. It's a way of representing data in both amplitude and phase space. And we can also use polarization. Light has different polarization. We can use orthogonal polarization and double the amounts of data that we transmit. So we play all these tricks, and together with a different wavelengths. So we can use different wavelengths, just like in radio. You tune your radio, well, now you do it digitally. The different frequencies, they carry different amounts of data. Now hundreds of wavelengths of data can be used. In fact, attenuation of what just defines the bandwidth that we can access is the attenuation of glass with wavelength. And so far, we've been using very, very tiny portion of all the achievable spectrum. So in fact, one of the major developments is to develop new amplifiers which have a much broader amplification window. We've been using these erbium doped fiber amplifiers. They only have 4 terahertz. 4 terahertz was considered, when I came to UCL and I wanted to set up a research laboratory in optical communications, we were told all the time that it is unnecessary. Nobody will want more than 4 wavelengths occupying 10 gigahertz. Now 4 terahertz is not enough. And 4 terahertz, so we now have to find new ways and new materials to expand the bandwidth, accessible bandwidth. And remember that in fiber, you can at least put another fiber in. In wireless communications, when you run out of wireless spectrum, that's it. There's no more spectrum. The end. And the wireless spectrum is much, much smaller than the optical spectrum. So So one of the questions is how to make best use of the available spectrum. I've already mentioned new amplifiers. So what of the records? And the records are very numerous. Everybody tries. Today, we ourselves report a milestone, 1 terabit per transceiver. One of my colleagues, Ligia Galdino, is sitting here, and she's been working with us. She's come all the way from Brazil to work with us on the development of our communications systems, the very major strides that we've made. But in the world, there are different criteria that have been used to judge total capacity on fiber, 100 terabits per second, but over a short distance. So the quest is to transmit a lot of capacity over a long distance. In the limit, it's always possible to transmit infinite amount of capacity, but over zero distance. So the largest capacity times distance product is 50 terabits over 9,000 kilometers approximately. So that's a trans-Pacific distance, 6,000 transatlantic, 9,000 is trans-Pacific. There is a big prize out given by the EU, 500,000 euros, to beat this record, or to beat the record achieved. We're going to have a go. I don't know if we'll manage, but in terms of spectral efficiency, the use of combination of different modulation formats, so different amplitude combined with phases, is 15 bits per second in 1 hertz of information. Different spatial division multiplexing, they're using fiber with multiple cores, or in fact many multiple, equivalent to many multiple fibers, is a petabit per second, but again over short distance, relatively short distance. Let me show you what a system like for this kind of transmission looks like. This is a system from our laboratory. It looks terribly complicated, and it is. It is. The technology is extraordinary. We generate one signal, which we then able to multiply into a comb of different wavelengths called a super channel. So multiple wavelengths are then modulated by a pair of modulators and transmitted into, we use a recirculating loop, because it's quite difficult, even with small spools of fiber, it is difficult to fill. I don't know if you've encountered, we in UCL are very short of space. It is very difficult to get enough space to have 9,000 kilometers of fiber to simulate trans-Pacific transmission. So we built a recirculating loop, which is about, it's whatever we want it to be. It's now about 80 kilometers long, and then we recirculate the data around it to simulate very long distance transmission. And then we receive it all together. The trick to receive all these wavelengths together, this is the milestone that we've achieved today, over 1 terabit per second received together simultaneously using a super receiver, which is able to receive both phase and amplitude information. And then once we can completely describe the signal by phase and amplitude, we can process it digitally. We can digitally manipulate it against the kind of distortions that I talked about, both linear and nonlinear. So this is what the spectrum looks like. And then it's quite messy. This is a constellation diagrams. All the dots should be separate. The ones we sent are separate. They've been received, they're messy, and now we have to manipulate the data from this mess to clean it up through a series of digital processing steps to clean it up to its original state. And indeed, if we only use electronic processing, only linear, cleaning up only linear distortion, we can transmit over maybe 4,000, 3,000 kilometers. If we can use the nonlinear distortion called digital backpropagation works in the following way. You receive the signal, you have its phase and its amplitude information, and then you send it digitally on a reverse journey to undo all the distortion that you've acquired. Then we're able to, by collecting the whole signal together, all the different components, we're able to almost double the transmission distance over which we transmit and get across the transatlantic distance. And you could see this. It was messy to start off with, and when we do multi-channel DBP, we've cleaned it up and are able to deal with it. So this is our paper that's out today, 1.125 terabit per second super channel. It's on the UCL, I'm told it's on the UCL website as a press release. It's approximately 50,000 times faster than superfast broadband. Do you know what your superfast broadband speed is? Anybody know? It's 20. How much?
100 megabytes or more?
Superfast broadband is defined as anything higher than 24 megabits per second. So it's quite modest, it's hardly superfast. And that means that you can transmit. I don't know if any of you watch Game of Thrones. Anybody heard of Game of Thrones? Well, very good. So you can download the entire series, a whole series of Game of Thrones in 1 second. So that's quite fast. I'll skip the details. Again, it's complicated to code the data in a particular way, to impose that coding on the optical channel, modulate it, transmit it, double its capacity through polarization multiplexing with the different, this is equalize the different wavelength components, and then it is possible to, by forward error correction processing, get it to below the error rate for where it can be reconstructed. It's complicated business, but it's one which will ensure that really people's lives are transformed through services which are not available now and will not be available through the kind of incremental steps that are evolving. The ultimate limits actually to transmission capacity are not known. They were defined, there was a paper published by Claude Shannon. This year sees another anniversary, 100 years from his birth. He's a brilliant mathematician and engineer, and he defined a so-called Shannon limit, which defines the capacity of any channel. And this, we've been trying to work out what is the capacity of a nonlinear channel. Even when, these are graphs for the achievable capacity against power. So the more power you put in, the more Shannon limit says that the spectral efficiency, or the amount of information, is proportional to log 2, the log base 2 of approximately the signal to noise ratio. The signal is equivalent to the power you put in, and the noise is the noise from the amplifiers that one acquires. And it may be possible to transmit a petabit, but again, there is this drop in capacities due to nonlinearities. We're able to increase the sensitivity to nonlinearities, make the fiber more impervious, or transmission more impervious to nonlinearities through these nonlinear processing techniques. But nonetheless, there is a limit. Eventually, the limit will be where the fiber will melt. But we're far from the limit. And apart from, I'm just coming to my last couple of slides, apart from point-to-point transmission, we are working on different timescales. Of course, optical networks occupy different timescales, from quantum communications and quantum computing to interconnection of qubits, to interconnection of processors, routers, and transmission and recomputing from nanometers to thousands and tens of thousands of kilometers. So they operate on different time and distance scales over 12 orders of magnitude. But they all have the same challenges: how to design networks and transmit and process data with minimum errors, delays, and resources, whilst maximizing the overall network capacity, and whilst taking the the physics of the channel into account. But what about how much data can a human process? Well, we've worked out that it may be possible to process 1 exabyte of data per year per person. And our brains are very efficient in coding this information. So we're trying to, perhaps in the next generation, to try and learn from the brain to build networks which are so efficient, because the capacity of the optic nerve is much, much lower. It's like 10 megabits per second. I finish on in the commemoration of the first anniversary that I talked about, that of the installation of transatlantic cable. So inspired was one of the master fairy tale writers, Hans Christian Andersen, that he wrote a fairy tale about it called The Great Sea Serpent, where he writes that this long, thin, infinitely long serpent is the most wondrous creature of our seas. It is conceived and born by human genius, and human genius has laid it on the seabed, stretching it from east to west. And it is human genius that began directing messages along it, messages that travel faster than the time it takes for the light of the sun to reach the earth. Deep under the water, it has circled the earth, and like the Midgard snake, grasped its own tail. Other sea creatures cannot fathom quite what this wondrous being is that has descended, buzzing with thought of all mankind, speaking in all languages, and yet silent messenger of good and evil, wonder of wonders of our oceans, the great sea serpent of our time. So it is in commemoration of that I finish, and with also thanks to the genius of man and woman, and my colleagues in my lab, with thanks to them and our research fellows, our brilliant students, and who are developing the next generation of optical communications, which will not have infinite capacity, but will try at least to approach the limit. And also with thanks to UCL, who's given us a home to build to what is now one of the best and most inspirational optical communications laboratories in the world. And thank you to you for coming and listening.
Thank you so much, Polina. We do have a couple of minutes of questions if you've got one. If you could just wait for a microphone to come to you so people can hear you online.
I don't know if you can answer this question, but Wi-Fi. Everywhere I go, people have supposedly, this is what I complain about Virgin Media as well, I've been with them for so many years, before it was called Blue Yonder and Cable London. They advertise broadband, but yet when you're on a Wi-Fi, you hardly get 65 megabits per second, and sometimes you get 39 or even less. That can't be fast enough. What would be the solution?
I'm so glad you've asked that. This is a disaster. We have 1 terabit per second working in our labs. We can build systems that have 100 terabits to 1 petabit of capacity, and yet you are all forced to, even when you purchase from whichever provider provides you with this, the highest possible capacity, you won't get it for 2 reasons. One, statistical multiplexing, where operators do not really they don't want to over-provision the network. Competition doesn't always lead to better service. That leads to underinvestment in the network. And they don't want to over-provision the network. So they say, well, during the day, the capacity isn't really used very much. And when people come home, well, okay, for a couple of hours. It's 3 o'clock in the morning, I guarantee you'll get your capacity. But also, there's a legacy problem. There's a problem of legacy. Routers, domestic routers, work for many years. I don't know how often you upgrade your router, but they're quite slow. And there is a big legacy system in the domestic equipment, and that also constrains the capacity.
Also, very quickly, is it Ofcom? They're going to decide within the next 6 weeks what's going to happen to BT Open Zone.
OpenReach.
Is it OpenReach?
Yes.
Oh, you know about that? Yeah.
Well, I'm sorry. I'm an academic professor of engineering. I'm not professor of economics of telecoms. But there is a wonderful colleague that I have called Jonathan Haskell in Imperial College who works on economics of telecommunications. He, I'm sure, will be, if he's listening now for this lecture being streamed, will be able to answer your question in full. Yes, at Imperial College, yes.
Thanks so much.
I don't want to advertise the competition, of course. But
I'm afraid that is all we've got time for. There's a 2 o'clock lecture in here, so I'm afraid we have to move out. But thank you so much for coming. Thank you mostly to Professor Polina Bayvel.
I'm very happy for anybody who wants to answer questions afterwards.